We are asked to find the general solution of this differential equation y double prime minus y equals e raised to x plus 2e raised to 2x. So first, we will equate it to 0, y double prime minus y equals 0. So first, y equals e raised to mx, then y prime equals m e raised to mx, and y double prime equals m squared e mx. Then we will substitute this to this equation. So m squared e mx minus e raised to mx equals 0. Then we will factor out e raised to mx. Quantity m squared minus 1 equals 0. So e mx equals 0, then m squared minus 1 equals 0. We will factor out this. So m minus 1, m plus 1 equals 0. So our roots is m equals 1 and m equals negative 1 using case 1, real distinct roots. So the root m equals negative 1 gives y1 equals c1 e raised to negative x. The root m equals 1 gives y2 equals c2 e raised to x. So our complementary solution yc equals c1 e negative x plus c2 e raised to x. yc equals c1 e raised to negative x plus c2 e raised to x. So assume that our particular solution is a1 x e raised to x plus a2 e raised to 2x. Then compute d squared y over dx squared. So d squared over dx squared of our particular solution a1 x e raised to x plus a2 e raised to 2x. So our y double prime here is a1 2e raised to x plus x e raised to x plus 4a 2e raised to 2x. So we will substitute it to the differential equation y double prime minus y equals e raised to x plus 2e raised to 2x. So a1 quantity 2e raised to x plus x e raised to x plus 4a2 e raised to 2x minus quantity a1 e raised to x plus a2 e raised to 2x equals e raised to x plus 2e raised to 2x. So simplifying this further, we get 2a1 e raised to x plus a1 e raised to x plus 4a2 e raised to 2x minus a1 e raised to x minus a2 e raised to 2x equals e raised to x plus 2e raised to 2x. So cancel this, we get 2a1 e raised to x plus, so the same terms, so 3a2 e raised to 2x equals e raised to x plus 2e raised to 2x. Then we will find the value of a1, so 2a1 equals 1, ex and ex, comma, 3, a2 equals to 2. So we get a1 equals to 1 half, then a2 equals to 2/3. So we get our particular solution in this is 1 half x e raised to x plus 2/3 e raised to 2x. So y equals yc plus yp. We get c1 e raised to negative x plus c2 e raised to x plus 1 half x e raised to x plus 2/3 e raised to 2x. That is our y. So again, we are asked to find the general solution of this differential equation y triple prime minus y double prime minus y prime plus y equals f of x. But this time we will use the variation of parameters. So first, let y equals e raised to mx. So our y prime equals m e raised to mx. Y double prime equals m squared e mx, and our y triple prime equals m cube e raised to mx. Then we'll first equate it to 0. Y triple prime minus y double prime minus y prime plus y equals 0. Then substituting the values, so m cube e raised to mx plus m squared e mx, minus, minus m e mx plus e mx equals 0. So we will factor out e raised to mx, so we get m cubed minus m squared minus m plus 1 equals 0. So e raised to mx equals 0. Then m cubed minus m squared minus m plus 1 equals 0. So we'll factor it out. So we get m minus 1 squared quantity m plus 1 equals 0. So m minus 1 equals 0. Then m plus 1 equals 0. So from this, we get our m, values of m. We have m equals 1, m equals 1, and m equals negative 1. So by case 1 and case 2, real distinct roots and real repeated roots. So next, the root m equals negative 1 gives the value of y1, which is c1 e raised to negative x. The root m equals 1 gives the value of y2, which is c2 e raised to x. Since this is repeated, our y3 is c3x e raised to x. So our complementary solution for this is c1 e raised to negative x plus c2 e raised to x plus c3 x e raised to x. So list the basic solutions for the yc. So our yb1 equals e negative x. YB2 equals e raised to x. Then our YB3 equals x e raised to x from these values. So, using Wronskian matrix of this YB1, YB2, and YB3, we will solve for our W, which is e negative x, then negative e. So, we already derived this. So, e negative x, e raised to x, e raised to x, e raised to x, then x e raised to x, then e raised to x plus x e raised to x, then 2e raised to x plus x e raised to x. So using the basket method, so we get the value of this is 4e raised to x. Okay, our next step is we get our W1 using Wronskian method matrix again. So first, the W1, we will let 0, 0, and f of x. Next is e raised to x, e raised to x, then e raised to x. And the third column is x e raised to x, e raised to x plus x e raised to x, then 2e raised to x plus x e raised to x. Using the basket method, we get e raised to x quantity, e raised to x plus x e raised to x, f of x minus e raised to x quantity x e raised to x, f of x. Simplifying it further, we get e raised to 2x, f of x. Next is we get our W2. So, this W1, we let 0, 0, f of x. So, the next is the second column. We let 0, 0, f of x. Then, go back again. E raised to negative x. Negative e raised to negative x. E raised to negative x. X e raised to x. E raised to x plus x e raised to x. 2e raised to x plus x e raised to x. Using the basket method again, we get negative e raised to negative x, x e raised to x of f of x minus negative e raised to negative x of e raised to x plus x e raised to x, f of x. So simplifying it further, we get negative 2x minus 1, f of x. The last one is we get our W3. So our W3 is, so first, the first column is as is, negative. So e raised to negative x, then here e raised to x, e raised to x, e raised to x. Then the third column is 0, 0, f of x, just like we did W1 and W2. So using the basket method again, we get 1 f of x plus 1 f of x. So we get 1 plus 1, 2 f of x. Then next is we let u1 of x equals to the integral of our w1 of x over the w that we get earlier, dx. So, our u1 equals to integral of e raised to 2x over 4e raised to x of f of x dx. Then we get 1/4 integral of e raised to x f of x dx. So our u1 here is 1/4 integral of e raised to x f of x dx. So we already solved our u1, so the next step is let our u2 of x equals the integral of w2 of x over w dx. So we get the integral of negative 2x minus 1 over 4e raised to x f of x dx. So simplifying it further, we get 1/4 integral of e raised to negative x, this, and quantity negative 2x minus 1 f of x dx. So the third one is let u3 of x equals to the integral of over w3 of x over w dx. So we get integral of 2 over 4e raised to x f of x dx. Then, to simplify it further, we get 1/2 e raised to negative x f of x dx. So our final answer of u3 is 1/2 integral of e raised to negative x f of x dx. So we already solved the u1, u2, and u3. So we get our particular solution, which is 1/4 e raised to negative x integral of e raised to x f of x dx plus 1/4 e raised to x integral of e raised to negative x quantity of negative 2x minus 1 f of x dx plus the u3, which is 1/2 x e raised to x integral of e negative x of f of x dx. So this is our particular solution. Then we get our complete solution, which is y equals yc plus yp. So our complementary solution was solved already using the case 1 and case 2. So our y equals c1 e raised to negative x plus c2 e raised to x plus c3 x e raised to x plus our yp, which is 1/4 e raised to negative x integral of e raised to x f of x dx plus 1/4 e raised to x integral of e raised to negative x quantity negative 2x minus 1 f of x dx plus the last one is 1/2 x e raised to x integral of e raised to negative x f of x dx. So we already solved our complete solution. In solving this problem, we'll first determine the energies that the problem possesses. So the potential energies plus the kinetic energies equals some constant C. So first we will determine the potential energy. So we will denote is as Pe1. So first potential energy that the problem possesses is the weight itself. So this is equal to the mgh. So weight, so recall that weight is equals to mg. But our weight in the problem is 2w. So 2w equals our height is negative y. So why negative y? Because we will assume in this problem that the positive direction of y is downward. So as y increases or y goes down further, our PE decreases. So since this PE increases as you go upward or you go further, so we will have our y this as negative. The next potential energy that the problem possesses is the spring. So we will denote is as PE2. For the spring, we have the integral of F ds. So recall that our F force is equals to the Ks. So using the Hooke's law, because it is spring. So, but our limits here is from this, the spring, we will denote this as beta. So, as it is stretched, so beta plus y. So our limits here is beta, from beta to beta plus y. So we will integrate this. So integral of beta from beta to beta plus y of our f is ks. Ks ds. So we'll integrate this with respect to s. So we have 1 half k s squared evaluated from b to b plus y. So we get 1 half k quantity of b plus y squared minus beta squared. So we will simplify it further. We get 1 half k quantity of beta squared plus 2 beta y plus y squared minus beta squared. So cancel, cancel. So we get our P2 is equals to beta ky. So simplifying further, ky plus 1 half ky squared. So the next step we're going to do is we will determine the kinetic energy. So our KE1 is the weight also because it is moving. So our weight, which is 2W. So recall that our kinetic energy is 1 half mv squared. But the derivative of our y prime is equals to v. So we have 1 half m quantity of y prime squared. So our m here is 2w 2w for the weight. So we have 1 half 2w over g, because w is equals to m g. We have solved our mass times y prime squared. So cancel, cancel. So we have w over g y prime squared. The next kinetic energy is for our bigger pulley. So we will denote this as KE2. So recall that our for our pulleys, it is moving. We will solve this by the moment of inertia. So 1 half I plus the angular velocity. Since our angular velocity is the same as y, so but our angular velocity is using theta, which is theta here is 1 half I theta prime squared. Next is we will solve our I here. So our I is, our inertia is equal to m r squared over 2. Our m for the bigger pulley is 2w. So over g times r squared over 2. So we get w over g r squared. So we will substitute the value to this ke2. So ke2 is 1 half Our I now is W over G R squared. Since we have this theta prime squared, so that we will cancel this R squared, we will assume that our theta is equals to Y over R. So theta prime is equals to Y prime over R. Do not mind this R because this is just constant. So times dy prime squared over R squared. So cancel. So we have 1 half W over G Y prime squared. So that is our KE2. For our KE3, which is the smaller pulley, so same process again, but this time our mass is W. So KE equals 1 half mv squared. So the same as is. So 1 half I omega squared. So for this, our the bigger pulley is equal just the same of our smaller pulley, but recall that the radius of our bigger pulley is not equal to the radius of our smaller pulley. So we denote that 1 half I is equals to 2 theta prime squared because the radius of our smaller pulley is times 2. Next, we'll solve for our inertia, which is inertia is equal to m r over 2 squared times 1 half, since the radius is divided by 2 because it is smaller. So our m here is W over G R squared over 4 times 1 half. So simplifying it further, we get R squared W over 8G. So our KE3 is equals to 1 half W over 8G times R squared times our theta prime squared is replaced by times 4 times Y prime squared all over R squared. So cancel, then 2 here. So simplifying it further, we have 1 half times W over 2G Y prime squared. So W over 4G Y prime squared. So this is our KE3 for the smaller pulley. Since we have 2 small pulleys, so KE3 is just equal to KE4. So we'll just double it. So the next is from the first equation that I gave, PE plus KE equals some constant C. So we will substitute all the values that we get at the very first. So our PE here is negative 2 WY plus beta KY plus 1 half KY squared plus W over G Y prime squared plus W over 2G Y prime squared plus W over 4G. This is for the smaller pulley. Y prime squared. So we will double it. W over 4G Y prime squared equals to C. The next step that we should do is we will derive it. So denote that that y is equal to y prime. So we have negative 2w y prime plus beta k y prime plus 1 half k 2y y prime plus 2w over g y y prime y double prime plus 2w over 2g y prime y double prime plus 2w over 4g y prime y double prime plus 2w over 4g y prime y double prime equals 0. So simplifying it further, we get negative 2wy. Oh, thank you for my sponsor for this pen. Y prime plus beta k y prime plus ky y prime plus 4w over g y prime y double prime. Since we will combine like terms, equals to 0. So from this, we will divide it by 1 over y prime. And we get negative 2w plus beta k plus ky plus 4w over g y double prime equals 0. From this, we will make this into a linear differential equation. 4w over g y double prime plus ky equals to 2w minus beta k. So to get rid of this beta, we have from the Hooke's law, F equals Ks. So we will assume that this S, the stretch spring, is just equal to this beta. So F is equals to K beta. So our F is 2W, which is K beta. So our beta now is 2W over K. So 4W over G y double prime plus ky equals 2w. So our beta minus 2w over k times k. So 0. So 0. So 4w over g y double prime plus k y equals 0. So we will divide this by g over 4w. So we get y double prime plus gk over 4wy equals 0. From our equation, we have y double prime plus omega squared y equals 0. So we will solve our omega here, which is omega squared equals to here the gk over 4w. To get our omega, we have square root of gk over 4w. Recall that our frequency, that is omega over 2 pi, so we'll substitute this value. So our omega now is this. So 1 half pi times gk over 4w. So this 4 we will extract this. So we have 1 over 4 pi square root of gk over w, which is in hertz. That is our final answer.